Hello my dear students, in this lecture we are going to see liquid vapor dome. Now here the meaning of this liquid vapor dome is nothing but whenever there is a conversion of liquid into vapor, then the zone obtained is called liquid vapor dome. Now here during this conversion, liquid is converting into vapor. That means we can say it is a phase change. The conversion of liquid into vapor is called vaporization, right? Therefore it is a phase change where liquid is converted into vapor. Now my dear students, phase change condition is also called saturation condition. Phase change condition is also called saturation condition. Saturation condition. Therefore we can say whatever may be the pressure during phase change is called saturation pressure, and whatever may be the temperature during phase change is called saturation temperature. And my dear students, corresponding to every saturation pressure there is a saturation temperature, and corresponding to every saturation temperature there is a saturation pressure. That means as saturation pressure, that is phase change pressure, increases, then saturation temperature, which is called boiling temperature or phase change temperature, also increases, and vice versa. Whenever this saturation temperature, that is phase change temperature, decreases, sorry, pressure decreases, then saturation temperature also decreases, means phase change temperature, which is nothing but boiling temperature, also decreases. Now my dear students, and during phase change we can say, during this saturation condition, during phase change, pressure and temperature remains constant. For ideal gas, during phase change, pressure as well as temperature remains constant. Therefore here this saturation pressure is constant, and corresponding to this saturation pressure, the saturation temperature is also constant during phase change. Therefore for phase change we can say the change in pressure will be equal to 0. Pressure is constant, means there is no change in pressure, as well as change in temperature will be 0, that is temperature is constant, means there is no change in temperature, right? Now my dear students, we have one Gibbs function. Now this Gibbs function is nothing but represented by capital G. Now this Gibbs function is nothing but G is equal to H minus Ts. H minus Ts, this is the Gibbs function, where H is enthalpy, T is temperature, S is entropy, right? Now that already we have seen in basic relations, thermodynamic relations, that is ideal gas equations, right? Now here G is Gibbs function, H is total enthalpy, then T is temperature, and S is total entropy. So as this Gibbs function G is equal to H minus Ts, now let us find change in Gibbs function. Change in Gibbs function is nothing but dg. Now here therefore change in Gibbs function is equal to dh minus, here it is a product of, here we can say it is a product of temperature and entropy. Therefore as temperature changes, entropy also changes, right? As Gibbs function changes, then enthalpy, in temperature and entropy both changes. Therefore here we have to do partial derivative, right? Therefore while doing partial derivative we will put temperature constant ds minus then entropy constant dt. This is how we are doing partial derivative in mathematics, right? Therefore this change in Gibbs function is equal to dh. Now we know that dq, heat is nothing but tds. Heat, from entropy topic, heat is nothing but tds. Therefore here tds can be replaced with, we can say dq, dh minus dq minus s dt. This is a change in Gibbs function. Now my dear students, here enthalpy, H is nothing but U plus PV, that already we have seen in thermodynamic relations, that is ideal gas equation. Therefore change in enthalpy will be equal to change in internal energy plus pressure constant change in volume plus volume constant change in pressure. Now here this PdV is nothing but work. PdV is nothing but non-flow work. Therefore dH is equal to du plus dw plus vdp. And my dear students, as per first law of thermodynamics, as per first law for a non-flow process, we can say dq is equal to du internal energy plus work. Therefore this du plus dw can be replaced with dq. Therefore here change in enthalpy is equal to dq plus vdp. Therefore dh minus dq can be written as vdp, right? So let us substitute this dh minus dq here, that is vdp. Therefore dg is equal to, here dh minus dq is vdp minus s dt, right? So my dear students, This is the formula for change in Gibbs function, right? And we have seen just now during phase change. What is the meaning of phase change? Phase change is nothing but where pressure and temperature both remains constant. Means during phase change pressure is constant, temperature is constant. That means change in pressure is 0 and change in temperature is 0. So during phase change, this Gibbs function dg is equal to vdp minus es dt. And my dear students, as during phase change in pressure is 0, change in temperature is 0, therefore this change in Gibbs function is 0, right? Therefore my dear students, the meaning of phase change is nothing but change in Gibbs function is 0. That means Gibbs function is constant. Gibbs function is constant, and whenever Gibbs function is constant, then pressure and temperature is always constant. Now during phase change, that is conversion of liquid into vapor, if I draw pressure versus volume and temperature versus entropy diagram, here let us draw the pressure versus volume, and another temperature versus entropy diagram, TS diagram, temperature versus entropy diagram. Now my dear students, the liquid vapor dome you will find like this. Here the liquid vapor dome will be like this. It is called liquid vapor dome. Again on TS diagram, the dome will be like this. On TS diagram, this is the liquid vapor dome. That means for this dome, to the left side of this dome, there is a liquid state. Here we can say to the left side, there is only liquid state, liquid, that is L. And to the right side of this dome, there is a vapor state. There is a vapor state, that is V. And in this liquid vapor dome, the content will be in wet state, that is liquid plus vapor state, liquid plus vapor state, that is called wet state, wet zone or wet state, right? Similarly for TS diagram also the same meaning is there. Here left side is liquid dome, liquid, right side is vapor, and in between liquid plus vapor, that is wet state, right? Now my dear students, here this line is called saturated liquid line up to one point, that is the peak point. Here there is a one peak point, and corresponding to this peak point, let us say this peak point is called critical point. Here peak point is called critical point, CP. In both diagram critical point is a peak point, right? And the corresponding pressure to the peak point is called critical pressure. Here corresponding pressure is called critical pressure, and corresponding volume is called critical volume, VC. And corresponding temperature to the peak point is called critical temperature, TC. Critical temperature, TC. Now my dear students, to the left of this critical point, right, to the left of this critical point, this is saturated liquid line. Means on this line dryness fraction is 0. Dryness fraction is 0 means dryness fraction is nothing but mass of vapor divided by mass of vapor plus mass of liquid. Means on this left side line, the mass of vapor is 0. There is no vapor molecule, only liquid molecule. That means dryness fraction is 0, right? Therefore, and the locus of all these zero dryness fraction points, the locus of all these zero dryness fraction points is called saturated liquid line. Therefore here this left side line is called saturated liquid line. Therefore this line we can say saturated liquid line, from which phase change starts. From this line there will be a phase change, means after that the liquid will start converting into vapor, we will get liquid vapor dome. And the right side to this critical point, this line is called saturated vapor line. Means on this line dryness fraction is equal to 1, quality is 1, dryness fraction is also called quality. That means dryness fraction is 1 means here mass of liquid is 0, means it is a dry saturated vapor line. The locus of all such dryness fraction is equal to 1 point is called dry saturated vapor line, right? Therefore this locus of all such dryness fraction is equal to 1 is called dry saturated vapor line. Therefore this line is dry saturated vapor line, right? And on TS diagram also the same meaning. On TS diagram also, here this line critical, the left line to the critical point is called saturated liquid line, right? And right side line, here this right side line to the critical point is called saturated vapor line, dry saturated vapor line, we can say vapor line. Now for this saturated liquid line, as volume goes on increasing, pressure also goes on increasing. Therefore you can see as volume is increasing, pressure is also increasing. Therefore it is having positive slope. And for dry saturated vapor line, as volume goes on increasing, pressure goes on decreasing, right? Therefore it is negative slope. As well as on temperature versus entropy diagram, for this saturated liquid line, as entropy increases, temperature increases. Therefore as entropy increases, temperature increases, therefore positive slope. And for saturated vapor line, that is dry saturated vapor line, that is dryness fraction is equal to 1, as temperature decreases, entropy increases. As temperature decreases, entropy increases. Therefore it is having negative slope. It is having negative slope. Therefore we can say the slope of saturated liquid line is positive and the slope of dry saturated vapor line is negative, right? Saturated liquid line will be having positive slope and dry saturated vapor line will be having negative slope, and the positive slope is becoming negative slope. So first it has to become 0. Therefore we can say at critical point the slope is 0. At critical point slope is 0. Later we are going to discuss about this critical point because this is very important point in the diagram, right? Now generally whenever there is heat addition and heat rejection during steam, then these are constant pressure processes. So let us discuss here constant pressure process on PV and TS diagram. Now at constant pressure, if heat is supplied, then volume increases. So my dear students, the constant pressure process on here PV diagram will be like this: straight horizontal line, constant pressure process. This is constant pressure process. And during phase change, the pressure is always constant. So in liquid vapor dome, pressure is constant here. Alright. So my dear students, here I am considering few points. Let us say point A. Let us say point A in liquid region. Let us say point B on saturated liquid line. Point B is on saturated liquid line. Point C in liquid plus vapor state, that is wet region. Point D on saturated vapor line, and point E in vapor state. Point E in vapor state. Because later we are going to do analysis of point A, B, C, D and E. Now let us draw these lines on temperature versus entropy diagram. So my dear students, whenever we heat at heat supplied, volume is increasing. Therefore whenever heat is supplied at constant pressure, both temperature and entropy increases in liquid region. Therefore the line will be like this. In liquid region there will be a point A in liquid state and point B on saturated liquid line, right? And my dear students, from point B there is a liquid vapor dome, and liquid vapor dome means conversion of liquid into vapor. And just now we have seen during this conversion of liquid into vapor, that is during this phase change, there is a constant pressure as well as there is a constant temperature. During phase change, temperature as well as pressure remains constant. Therefore in liquid vapor dome, the constant temperature and constant pressure lines look like similar, right? Therefore there will be a C state, that is liquid plus vapor state, wet state. And on dry saturated vapor line there will be a D state, point D. And my dear students, in vapor state, whenever heat is supplied at constant pressure, temperature and entropy both increases. Therefore the line will be like this, right? The line will be like this. Therefore there will be a E state. And here these lines from A to E, we can say from A to E, right? It is a constant pressure process only, constant pressure process only. And during phase change the pressure is called saturation pressure. Therefore my dear students, it is a saturation pressure, P sat. And corresponding to the pressure, the saturation, there is always saturation temperature. During phase change from B to D there is a saturation temperature. Therefore from B to D the temperature is called saturation temperature. Therefore temperature at B, C and D is saturation temperature. Now my dear students, let us understand the various points, that is point A, B, C, D and E on this PV diagram, in this PV diagram as well as temperature versus entropy diagram. So my dear students, here we are going to understand these various points, right? Now the point A is nothing but liquid state. The point is A is nothing but liquid state, right? Therefore let us understand the points one by one. Number one, state A. Whatever may be the state A, it is liquid state. It is called subcooled state, or it is also called compressed liquid state. It is, we can say, subcooled state, right? Subcooled state or compressed liquid state. Compressed liquid state. See my dear students, what is the maximum value for volume for liquid state? The maximum volume for liquid state is volume at B. After that there is liquid plus vapor. The maximum volume is volume at B. Therefore volume at A is less than volume at B. Therefore it is called subcooled state or compressed liquid state, right? Temperature is less than saturation temperature, hence it is called subcooled state, and it is also called compressed liquid state. Now my dear students, here we can say Ta, temperature at A is less than saturation temperature. Look at the Ts diagram. In Ts diagram you can see saturation temperature is more than Ta. Therefore degree of subcooling, here we can say degree of subcooling is nothing but difference between this temperature, that is saturation temperature minus Ta. Now my dear students, in subsequent topics we will understand subcooling process, and subcooling is nothing but subcooling is a process of decreasing the temperature at constant pressure below saturation liquid, right? Means here for subcooling pressure is constant and we are decreasing temperature below saturation temperature, means temperature is less than saturation temperature. This process is called subcooling, and this is generally done in compressors, right? In VCR cycle or in Rankine cycle or in Brayton cycle we are going to understand subcooling, right? It is done in compressors, and in during subcooling what is the purpose? The purpose is at constant pressure decrease the temperature below saturation temperature. Now second state is state B. State B is nothing but it is saturated liquid state. It is saturated liquid state. That means my dear students, on this saturated liquid line dryness fraction is equal to 0. Therefore state B is saturated liquid state. And my dear students, all the saturated liquid states are represented by symbol EF. The suffix is used EF. Suffix used is EF for saturated liquid states. That means the enthalpy at B, whatever may be the parameter on this saturated liquid line, enthalpy, entropy, internal energy, or entropy, or let us say specific volume, all parameters are represented by EF. Therefore enthalpy at B is HF, entropy is SF, then internal energy is UF, and specific volume is VF, and these values we are going to calculate from steam table. For this saturation pressure or saturation temperature from steam table, they will provide you values of HF, SF, UF, VF, and you must understand that these values are corresponding to saturated liquid line. Means on saturated liquid line the suffix EF is used. Therefore this is a very important note, for saturated liquid line the suffix EF is always used, right? And my dear students, here for the saturated liquid line dryness fraction is 0, and if I consider various zero dryness fraction points at various pressures, means if I change pressure then I will get this B point at different locations, right? And the locus of all these zero dryness fraction points is called saturated liquid line, and we have seen the slope of this saturated liquid line is positive. Now third state is, that is state C. Now my dear students, state C is nothing but liquid plus vapor state. Here the content will be partly in liquid form and partly in vapor form. Therefore the dryness fraction will be 0 to 1 any value. The dryness fraction will be having 0 to 1 any value. Now the liquid portion will be having liquid properties and vapor portion will be having vapor properties. And my dear students, this is called wet state. This state is called wet state. And my dear students, during this wet state we cannot apply PV is equal to MRT. That means ideal gas equation is not valid. We can say this equation is not valid because this equation is only for the vapor state or gaseous state. This is ideal gas equation, but in this wet state there is a liquid as well as vapor. So this PV is equal to MRT is not valid in this liquid plus vapor dome. Now next fourth state is state D. State D, and here state D is on dry saturated vapor line. Therefore it is dry saturated vapor state. This state is called dry saturated vapor state, right? That means on this state dryness fraction is equal to 1, right? The quality is 1. And my dear students, if at different pressure, if I plot these points, right, here we will get different points, and the locus of all this dryness fraction is equal to 1 point is called dry saturated vapor line, and the slope of this dry saturated vapor line is negative. On TS as well as HS diagram, PV diagram, we have seen the slope of this dry saturated vapor line is negative, and this dry saturated vapor line in steam table is represented with suffix G. Here we are using suffix G. Means whatever may be the parameter on this dry saturated vapor line, it is represented by suffix G. So pressure on this line is Pg. Pressure on this line is Pg, which is nothing but saturation pressure. Temperature on this line is Tg, which is nothing but saturation temperature. Right. Then as well as the enthalpy on this line is Hg. Internal energy on this line is Ug. Entropy on this line is Sg. And specific volume on this line is Vg. Therefore, G parameter is for dry saturated vapor line. Therefore, we can say, very important, this dry saturated vapor line is represented with parameter G. Now, last state is state E. Now, state E is in vapor state, means it is called superheated state. Therefore, fifth state, that is state E, it is called superheated state. State E, it is superheated state. Superheated state. Now, therefore, here we can say for superheated state, the temperature at E is more than saturation temperature. Is more than saturation temperature. Now, my dear students, therefore, it is called, the difference is called degree of superheat. The difference is called degree of superheat. Superheat, right? And this is nothing but TE minus T set. This difference is called temperature at E minus saturation temperature. And my dear students, again in subsequent topics we will understand one process which is called superheating. There we will be having superheating process. Now this superheating process we will understand in Brayton cycle, Rankine cycle, as well as in refrigeration cycles. Now superheating is nothing but, superheating is a process of increasing temperature at constant pressure above saturation pressure. Here this is a constant pressure line. We are drawing this constant pressure line on TS as well as HS diagram, TS as well as PV diagram. Now superheating is a process where at constant pressure temperature is increased and the temperature is more than saturation temperature. This process is called superheating process. Now my dear students, whenever heat is supplied at a temperature less than saturation temperature, observe temperature versus entropy diagram. In this temperature versus entropy diagram, let us observe this temperature versus entropy diagram. Right. Now my dear students, whenever heat is supplied at a temperature less than saturation temperature, means we can say A to B, we can say A to B, then the heat is responsible for temperature change. Whenever heat is supplied at a temperature less than saturation temperature, then the heat is responsible for the temperature change, and such a heat is called sensible heat. Therefore, heat between A to B is sensible heat. It is sensible heat, which is represented as SH, which is responsible for temperature change. And my dear students, whenever heat is supplied at saturation temperature, means during phase change, whenever heat is supplied during phase change, saturation temperature means phase change, that is B to D, then this heat is called latent heat. Therefore, heat between B to D is latent heat. That means the heat is responsible for phase change, denoted by LH. And my dear students, whenever heat is supplied at a temperature more than saturation temperature, then that is D to E, then it is called superheat. Again, this heat is responsible for temperature change, but the temperature change is in vapor state, right? Therefore, this heat is called superheat, right? Also called sensible heat. Superheat is nothing but sensible heat. Therefore, heat between D to E is responsible for change in temperature of vapor, increase in temperature of vapor. Therefore, it is superheat. Superheat. Similar to, superheat is similar to sensible heat, but sensible heat is temperature change of liquid and superheat is temperature change of vapor, and latent heat is a phase change of liquid to vapor or vapor to liquid. Now my dear students, the critical point in PV and TS diagram is very important parameter. So let us discuss about this critical point. Now here if I draw temperature versus entropy diagram, on this temperature versus entropy diagram, let us find this critical point. Now on this temperature versus entropy diagram, there is a saturated liquid line having positive slope. Just now we have seen this is a saturated liquid line having positive slope, and there will be a saturated vapor line. This is having negative slope. The slope of saturated vapor line is negative, and this line is called, we just now we have seen, saturated liquid line. Liquid line on which dryness fraction is 0, and this line is saturated vapor line. On this line dryness fraction is equal to 1, right? Quality is 1. And my dear students, the point where this saturated liquid line and dry saturated vapor line meet is called critical point. Here the intersection of saturated liquid line and dry saturated vapor line is called critical point. That means the point where positive slope becomes equal to negative slope, right? Here the point where slope changes its direction from positive to negative is called critical point. Therefore these are very important definitions regarding critical point. The first definition of critical point is the point where saturated liquid line meets saturated vapor line is called critical point, as well as the point where positive slope becomes negative and the negative slope becomes positive is called critical point. Therefore the slope at critical point is 0. Therefore zero slope point is called critical point, right? We can say zero slope point. Zero slope point is called critical point, and zero slope point is called point of inflection. It is called point of inflection. The point of inflection is called zero slope point. Therefore critical point is also called point of inflection or zero slope point. And the temperature at critical point is called critical temperature. Temperature at critical point is called critical temperature, and the pressure at critical point is called critical pressure. And my dear students, for water we can say this critical temperature at critical point is 374 degrees Celsius, 374 degrees Celsius, and pressure at this critical point is 221.2 bar. This is the condition at critical point, right? At critical point pressure is 221.2 bar and temperature is 374 degrees Celsius. That you have to remember these parameters, my dear students, very very important. Again, my dear students, at critical point, here to the left of this critical point, here this is a saturated liquid line. Below this critical line, here I have drawn critical temperature line. Below this line and to the left of this saturated liquid line, the state is liquid state. Here there is a liquid state, right? And between this dome there is a liquid plus vapor state, and outside this dome, right side of this dome is vapor state. Below this critical temperature line and outside this dome there is a vapor state, right? That means, my dear students, at a critical point we can say the liquid directly flashes into vapor, right? Therefore this is also very important definition. At critical point liquid directly flashes into vapor, hence latent heat at critical point is 0. Therefore we can say latent heat at critical point is 0. See, my dear students, as pressure goes on increasing, as saturation, we can say, just now we have seen in previous lecture also at the start of this lecture, as saturation pressure increases, saturation temperature also increases. But my dear students, because of this, latent heat goes on decreasing. Let's observe here. If I draw constant pressure line, let us say P1 constant line. Here this is the constant pressure line. Let us say on this line pressure 1 is constant, right? And here there is some one saturation temperature T1, T sat 1, right? And latent heat is nothing but here phase change heat. Therefore on saturated liquid line the values are called EF lines, EF values. Therefore whatever may be the enthalpy at this point, this enthalpy is HF, right? On saturated liquid line the enthalpy is HF, and on saturated vapor line the enthalpy is Hg, enthalpy is Hg. Therefore this difference is Hg minus Hf, which is called HFG, right? Here this difference of enthalpy HFG, HFG is nothing but Hg minus Hf, means enthalpy difference during phase change, which is called latent heat. This is called latent heat, my dear students. This is your latent heat, right? So let us understand this. As saturation pressure increases, saturation temperature also increases, but latent heat goes on decreasing. Let us observe here. If I draw at different pressure, at higher pressure, see here the latent heat is going decreasing. Here P2 is more than P1. Here P2 is constant. On this line P2 is constant. P2 is more than P1. Therefore saturation temperature 2. Here T sat 2 is more than T sat 1. Can you observe here T sat 1 is less than T sat 2, and slowly the latent heat is going on decreasing. Therefore can you observe here, as I go on at critical point latent heat becomes 0, means as saturation pressure increases, saturation temperature increases, and the latent heat goes on decreasing, and at critical point the latent heat becomes equal to 0. This is very important. Therefore critical point is a point where latent heat is 0, and latent heat is nothing but a phase change heat. Therefore the heat required for phase change from liquid to vapor is 0. That means at critical point liquid directly flashes into vapor. Now my dear students, in single phase region, that is let us say liquid region or vapor region, on TS diagram, in liquid state, as the temperature increases entropy increases, means this line will be having positive slope, right? In liquid state, as temperature increases, entropy increases. Therefore, in single state region, slopes are positive. In vapor state also, as the temperature goes on increasing, entropy goes on increasing. Therefore, this line will be having positive slope, right? Positive slope. Therefore, we can say in single phase region, the slopes are positive, but in two phase region, that is in this liquid plus vapor dome, as temperature in here during phase change, temperature as well as pressure is constant. Therefore, this is having constant slope. During two phase region, slopes are constant. Therefore, it is very important statement. In liquid vapor dome, the slope is constant, but in liquid and in vapor dome, the slopes are positive. Now, at this critical point on PV as well as TS diagram, the slope is 0, right? Therefore, the condition of critical point here, we can say at critical point slope is 0, means change in pressure with respect to change in volume at critical point is 0. And as well as, my dear students, on PV diagram, on pressure versus volume diagram, here the double derivative of this P and V is also 0. That means d2p divided by dV square is also 0 at critical point. At critical point, these two conditions must be satisfied for critical point. Must condition. This is a must condition for critical point on PV diagram. On temperature versus entropy diagram, dt by ds is 0 only. On temperature versus entropy diagram, dt by ds at critical point is equal to 0. But on PV diagram, single derivative of PV, that is dp by dv, is 0, as well as double derivative d2p by dv square at critical point is 0. Now, my dear students, beyond this critical temperature, it is called superheated gas. Therefore, here beyond this critical temperature, above this line, there is a superheated gas. Here there is a superheated gas. We can say superheated gas. And my dear students, between this dry saturated vapor line and below this critical temperature line, it is called superheated vapor. Therefore, here in this region, it is called superheated vapor. Superheated vapor state, right? Vapor. Therefore, superheated gas is beyond critical temperature and below critical temperature, and in vapor state it is called superheated vapor. My dear students, in case of this superheated gas, the molecular separation is very high and hence ideal gas behavior is applicable. Therefore, in superheated gas region, we can say in superheated gas region, the molecular separation is very high and the ideal gas equation, that is PV is equal to MRT, is valid, applicable, right? And in superheated vapor region, here in this superheated vapor region, the molecular separation is not so high and hence the ideal gas behaviors are approximated, right? In superheated gas region, 100% ideal gas relation is valid, but in case of superheated vapor region, the molecular separation is not so high, right? Hence the ideal gas behaviors are approximated. So in this superheated vapor region, PV is equal to MRT is again valid. We are using this relation. But my dear students, here, so let us understand here above this critical pressure there is a superheated gas, and in this superheated gas PV is equal to MRT. This equation is valid, right? Below this critical pressure and in vapor state there is a superheated vapor gas, and this PV is equal to MRT relation again valid. I mean, ideal gas equation we can use. But in this liquid plus vapor dome, this ideal gas equation PV is equal to MRT is not valid. This cannot be used. As well as in liquid state, this PV is equal to MRT is not valid. Thank you, dear students. In next lecture, we will see HS diagram, which is also called Mollier chart.